Hello, this is the second lecture in GPY 100, Physical and Environmental Geography. It is based on the second chapter of our textbook, Portraying the Earth. And in this lecture, I will speak about maps and computer cartography, geographic information systems, or GIS, geopositioning system, or GPS, and remote sensing and aerial photography, all various geospatial technologies that geographers use to portray both physical and cultural processes on the surface of our planet. This lecture has several learning objectives. First of all, I will describe and discuss the basic characteristics of map, their capabilities and limitations associated with different geographic projections. We would also learn in this lecture how to read topographic maps and how to interpret their symbols, scale, projections, location, and geographic coordinates. We would also discuss how computer cartography and GIS can be used to visualize and analyze spatial data. In this lecture, we would also familiarize with the Global Positioning System, or GPS, describe different types of remote sensing data, including aerial photography, optical data, thermal, microwave, and radar remote sensing, and discuss remote sensing applications in various areas. So this is an introductory geography class, and of course we are going to talk about maps. A map can be simply defined as a graphic representation of the real world. We all use maps every day, sometimes even without realizing this. Maps are used today in so many different apps that we use. They are guiding Google Maps. They're underlying Uber Eats. They're helping us to find location of the nearby restaurant. They're helping us to find directions to a friend's house. They're helping us to plan our vacation. Maps are absolutely everywhere, both in the paper form and more in the digital form. All of you have GPS in your cell phones today, and you all are probably using Google Earth or Google Maps in order to figure out the best directions to whatever place you are going, or just to find the location of the business or service that you are looking for. We are all looking at the map of our campus to find directions to the nearby class or to figure out where to park our car. So maps are really a part of our everyday reality. We rely on them so much that most of the time we are even not noticing this. So I'm going to pause for a moment, and I would suggest that just kind of browse internet on your computer. You can close this lecture and just go ahead to look for some maps, or you can look for maps on your phone and just take a moment to think how frequently you use maps just in one day. So it's important to realize that map is always an abstraction of the reality. Whatever map you use, it never shows you exactly the reality that it's meant to represent. And this is why we need cartography. Cartography is both science and art of making maps. It's a field of knowledge that studies map constructions. There are two broad categories of maps: reference maps and thematic maps. So as right now, I'm going to make a short pause. Please go online and find a few reference maps and a few thematic maps. So reference maps, as you probably have already found, normally show natural and human-made objects from the geographical environment with an emphasis on location. They don't provide much of in-depth information about anything else. They really just show the most prominent geographic features because their goal is really to show you where you are and how to find correct directions. Google Maps, that you would find, of course, online, would be a prime example of reference maps. Examples of reference maps also can be found in many atlases, road atlases, topographic maps, or you can see an example of a reference map on this picture. Thematic maps, on the other hand, just as the word thematic tells us, are focusing on specific themes. They are depicting specific phenomena or relationships between those phenomena and their spatial distribution. So here is an example of a pressure map, which is a type of a weather or meteorological map. Other examples of thematic maps could be a map of vegetation or even a map of a specific species. It could be a map of museums or a map of restaurants or historical map or a map of precipitation. All these are various examples of thematic maps. A map that we can see on our computer screen or on the page of the atlas is of course a model of what we could see in the real world, and this is why it uses a scale, which is a mathematical fraction of the distance on the map and the distance on the surface of the Earth. A scale can be expressed in three different ways, such as representative fraction, for example, 1 divided by 1 million, or a verbal statement, such as 1 centimeter on this map equals 10 kilometers on the Earth's surface, or 1 inch represents approximately 16 miles, or as a graphical scale, which is looking as a bar showing you the ratio between the distance on the map and the distance in the real world. The scale, expressed either as a fraction or as a bar or sometimes both, is placed at the bottom corner on the right side of your map frame. When you read a map, it's important to make sure that you understand what is the meaning of this fraction and what is the meaning of this bar. In other words, what is the large scale and what is the small scale? What is the representation of this unit on the map in the relationship with the same unit in the real world? Look at these three maps. Which of these is the largest scale? Which of these is the smallest scale? The answer can be counterintuitive. The smallest scale is actually the one which is represented by the largest number in the fraction. So 1 divided by 100,000 is the smallest scale. It covers the largest area. And then 1 divided by 25,000 is covering much smaller area. So this is a much larger scale. So note what is happening to the amount of the area which is represented on the map when the scale is changed, as we are moving from 1 divided by 100,000 to 1 divided by 25. We are literally zooming into the map in such a way that the area shown on the map is reduced by 25%. You know already that the shape of our planet is ellipsoid, or rather geoid, which is an ellipsoid specific for our planet Earth. And so there is a certain challenge of how the surface of this elliptical shape could be transferred and represented on the flat surface of the map. In order to do this, cartographers use geographic projections. None of these projections can accomplish this transfer completely accurately. Geometrically, such transfer can be achieved in several ways, but always with significant distortions and losses of information. Cartographers can use a cylinder to develop cylindrical projections, a cone for conic projections, or the surface of the Earth centered on the North or South Pole in azimuthal projections. Azimuthal projections are typically used only for mapping areas in the Arctic or in the Antarctic, in the areas very close to the central point of the map, which is pole, North Pole or South Pole. Cylindrical projections would represent the globe as if it is projected on the surface of the cylinder. The cylinder then would be cut and opened, and so that it would become a flat map. The same would be with a cone if we use conical projection to project the surface of the globe on top of the cone, and then the cone would be cut along one of its sides, opened up, and then that would become a flat map. Of course, it all would lead to significant losses of information and significant distortions in different parts of the map. Based on those distortions, all the map projections can be classified into several groups, such as equivalent projections, that would maintain correct area but not shape, conformal projections that will maintain correct angle but not area, for example, very commonly used Mercator projection, and the majority of projections would be neither conformal nor equivalent, but rather compromised. So those are the compromised projections, such as another very popular projections, Robinson. The majority of projections that we use today are compromised projections. They use elements of conic and cylinder and other projections using different geometric shapes to achieve this transfer from the surface of the globe to the surface of the map, and they include elements of equivalent and conformal and various compromised projections. Both reference maps and thematic maps can be sometimes useful on their own. For example, we could use reference map to find our way in the city, or we can use a thematic map to check the weather conditions. However, in the majority of cases, today we use maps as a part of geographic information systems. Maps can give us way much more information if we could actually explore the relationship between different spatial phenomena rather than looking at separate pieces of information individually or separate layers of information individually. So GIS, or Geographic Information System, combines computer cartography and database management systems, helping us to overlay information about not just location, but also population, environmental data, demographic data, economic data, and so on and so forth, and understand how they're spatially related. A geographic information system includes three major components, or three subsystems. The first subsystem is the input system that allows for collection of data to be used and analyzed for some purpose. So this could include a digitizer, a camera. We can use data through the keyboard on your computer, even with voice. We can convert spreadsheets. We can bring data in a tabular form or in the cartographic form. We can use remote sensing data. We can use digital image processing systems in order to pre-process this remote sensing data and then enter to this GIS. This information can come from the census, it can come from various economic databases and so on. So this information that is brought into the GIS can come in a variety of different formats. It can be sometimes pre-processed to make sure that they're all compatible within the GIS software. The second major component is computer hardware and software systems that actually allow us to store, analyze, process data and retrieve them for a variety of different analytical purposes. Data can be changed, manipulated, edited, and they can be also brought onto your computer monitor. This data can be displayed both as maps and as attribute tables. So the beauty of the GIS is that it allows us to see the relationships between the databases and the information portrayed on the map. In other words, every point, every line, every polygon, or every pixel on the map is related to the descriptive data that can be quantitative or qualitative in the database management system. And finally, the third component is the output system that generates maps, images, reports, and all kinds of digital and hard copy reporting information that then we can retrieve from the GIS and share with others. GIS helps us to understand and visualize spatial relationships and correlations among different phenomena and understand how they are related. For example, this map is a result of overlay of two different maps. One of them is, of course, a map of tectonic plates. The other one is the map of earthquakes of different intensity. As we overlay these two maps, we can see clear correlations between the earthquakes and different types of boundaries of tectonic plates. One of the input subsystems in the geographic information systems is Global Positioning System, or GPS. You all are familiar today with GPS. GPS is available today on most of our cell phones, helping us to track location. You can also place, of course, GPS in your car or on your bicycle just to help you to find your place anywhere around the world. GPS consists of two parts: a GPS receiver, and this is what you can find on your cell phone or in your car, or you can buy the GPS device and have it handheld or on your bike or in your car. And the second half of the GPS is, of course, the network of satellites on the orbit. So the original GPS system is Navstar, that consisted of 24 satellites, that was developed in the United States. Today, a number of other countries also use GPS, and the countries of the European Union have a similar system called Galileo. When we use GPS, a minimum of 3 satellites is required for the triangulation. So the GPS is using the principle of triangulation, essentially measuring the distance between you, your receiver, that can be in your car or on your cell phone, and the location of each of these 3 satellites on the orbit. The more satellites in the sky that are accessible for your GPS, the higher is the accuracy, but the minimum needed is 3. So when you start your GPS, sometimes you would see the signal acquiring satellites that might last for a few seconds, sometimes longer if it's very cloudy or if you are in the area with very dense tree canopy. It can take sometimes a little bit longer to connect. Once the connection is established, the GPS would actually measure the signal that is traveling from each of the satellites to your device, and would recalculate exactly your latitude, your longitude, and also elevation anywhere or above the Earth's surface from the signals that are transmitted by the satellites. Remote sensing is another geographic technique which is commonly used to gather data from space or from the airborne devices. Today we use remote sensing for a variety of different applications. Satellite remote sensing is another major source of geographic information coming in the digital form from satellite instruments. This is particularly relevant for physical and environmental geography because satellite remote sensing is using different bands of electromagnetic spectrum, such as visible light or thermal infrared or microwave or radar, in order to see specific phenomena in the lithosphere or biosphere or hydrosphere or atmosphere. So it really is extremely well suited for environmental observations, such as land use and land cover change, or loss of biodiversity, or atmospheric pollution, or climate change. Satellite remote sensing is using different wavelengths and measures how much energy is absorbed or reflected by different surfaces, making mapping extremely accurate. It also is extremely relevant for seeing the changes over time. For example, we can use remote sensing for mapping changes in the vegetation or mapping seasonal dynamic of agricultural crops or map specific geological rocks. Satellite remote sensing can be panchromatic. That means that it uses only one wavelength, only one band of electromagnetic spectrum. These images would appear as black and white. Of course, they provide significantly less information compared to multispectral, and especially hyperspectral data. Examples of multispectral data would be Landsat or SPOT. Multispectral data use multiple zones of electromagnetic spectrum. For example, visible light, multiple zones of visible light, such as blue, red, green, the infrared, near infrared, thermal infrared, to help us to see the differences in the behavior of the waves absorbed or reflected by different surfaces. For example, the difference of red and infrared is particularly useful for mapping green vegetation. And then hyperspectral data use even larger number of bands of electromagnetic spectrum. They use even larger number of wavelengths to portray different phenomena, such as, for example, MODIS, which is commonly used for a variety of environmental applications. Although the majority of environmental remote sensing data is coming today from satellites orbiting the Earth, some of it is also coming from airborne devices, such as drones and airplanes. These data can be also panchromatic or multispectral, and they can be also used for comparing situation over time. They can be used for tracking land use and land cover change. They can be used for urban planning purposes or just for understanding where things are. Photogrammetry is a branch of cartography that deals with obtaining reliable measurements and making maps from photography and aerial photography obtained, for example, from the instruments placed on drones or airplanes. These maps produced from the air photos can be oblique if they're taken at a certain angle, or vertical if the device taking picture is directly over the ground at the 90 degrees. These ortho maps can be multicolored, distortion-free. They are photographic images that are then processed and converted into maps when information about latitude, longitude, and some other features are overlaid with the air photo taken from an airborne device. Remote sensing data have many different applications. They're used in our everyday life for weather forecasting, agricultural surveys, forestry, geological survey, rangeland monitoring, commercial fishing, for pollution detection, land use planning, urban planning, erosion control, intelligence, military application, desertification control, atmospheric studies, and many other areas. Depending on the application, one might need data of high or low temporal or spatial resolution, or temporal or spatial scale. Temporal resolution or temporal scale means how frequently the data are obtained by the satellite. So the same phenomena or the same surface of the land can be scanned every few minutes or every few weeks or every few months, depending on our needs. For example, in meteorology, it's very important to have very high temporal resolution when we can see the same surface of the land captured every few minutes. On the other hand, spatial resolution shows us how detailed or how accurate is the surface on the land. How large is the area represented in 1 pixel of the satellite image. High temporal resolution is important in the applications that are focusing on the temporal changes. For example, in meteorology, high spatial resolution is more important in the application that are focusing on the details on the ground. For example, military applications, intelligence, or urban planning, where we need to see specific features on the ground, such as a car, a tree, a house, but we might be less concerned with the temporal resolution. As you can see, there is this huge number of international satellites that are managed by different countries, by different space agencies, different programs for a variety of different purposes. Some of the satellites are geostationary, such as GOES and many other meteorological satellites. That means that they're staying over the same side of the planet, over the geostationary orbit. Others are near polar satellites, such as NOAA. They're much closer to the surface of the Earth, and they're revolving over polar regions, scanning all sides of our planet, and they're used for a variety of different applications, such as land use, land cover change. Here is an example of satellite image of Hurricane Laura, obtained a couple of weeks ago, August 26, from the geostationary satellite GOES, which is used for weather observations. Here is another example of GOES imagery, again for meteorological application, showing us huge amount of water, huge amount of moisture forming over the Pacific Northwest past February, coming from the Pacific Ocean and then being dumped over Washington, Oregon, and California. So GOES was a good example of data with very high temporal resolution but low spatial resolution. GOES data don't really go very much into the details of the ground because they focus on the phenomena in the atmosphere. They're used for meteorological observations. On the other hand, for land use planning or for agriculture or for urban planning, we need data of much higher spatial resolution, not necessarily very high temporal resolution. So here is an example of SPOT. SPOT is a satellite developed by French Space Energy, and it's a false color image obtained from several bands of electromagnetic spectrum, showing us, of course, the Long Island in New York. And as you can see, this is a very high resolution data. We can clearly see specific blocks, we can see specific buildings, we can clearly see the coastal lines. And so this type of data is used, for example, by urban planners and land use planners. Here is another example of a very high resolution image from QuickBird that is typically used in urban planning. And this is the data that allow us to see individual trees and individual cars and houses, extremely high resolution of just 1 meter. For some other applications, such as monitoring climate change or land use and land cover change, we don't need very high spatial resolution. What we really need is the long-term archive of data in order to see how the situation has evolved. And so this is another very interesting example of remote sensing data. This is a data set from AVHRR, Advanced Very High Resolution Radiometer. It's an instrument or a series of instruments that have been orbiting the Earth on NOAA satellites since mid-1980s. And it's extremely useful because it has been around for such a long period of time, orbiting the Earth every day, twice a day, and so it's used primarily for monitoring vegetation using 5 spectral bands, including visible light, near infrared, and thermal infrared. So it's really focusing on green vegetation, on measuring biomass, on measuring productivity of the vegetation, and helping scientists to see how land use and land cover changed and how vegetation has changed as a result of climate change and probably some other impacts. So this is a great archive that you can actually find online. For many of you, it might really look like ancient history. It has been around for a very long period of time. In fact, I was a student when I started using this data. So here is another interesting example of environmental remote sensing that we can use, for example, to document climate change. This is an image from Landsat 8 taken this winter in February, showing you iceberg called B49 that is leaving the Antarctic glacier this February as a result of glacial melting. And to conclude, another example of Landsat 8, this time taken over Eastern Australia, also this February, showing you very dramatic changes from the period of wildfires and the drought, quickly turning into just as dramatic flooding that you can see on the eastern side of the image. So satellite remote sensing definitely offers us lots of useful objective environmental information that we can use at a variety of spatial and temporal resolutions, and it definitely helps us to study physical and environmental geography.